Hi, folks. We're going to get started here just in a few minutes. Going to wait for everyone to come in, and we'll probably get started at about 10:02, if that's all right. Hey, folks, just if you joined in the last couple minutes, we're probably going to start at around 10:02, just to give people a chance to trickle in here. So we'll get started just in a couple minutes. All right, I think we can get started. Prajay, can you put on the next slide for me? Thank you.
There you go.
So, hi everyone, and welcome to our webinar, An Introduction to Campbell Scientific's Sun-Induced Chlorophyll Fluorescence Measurement Solution, the FluoreSens 10. My name is Katie Kovacs, and I'm a marketing specialist here at Campbell Scientific, and I'll be hosting the webinar and directing the question period at the end. If you do have questions, I'd like to invite you to drop them in the chat, and we'll get to them after the end of the presentation. We have some time for that. Today's webinar will be presented by Prajay Prajapati, an application engineer and scientist for Campbell Scientific, and he was involved in the development of the FluoreSens 10 and has an expert level of understanding of the science of SIF. So I will turn it over now to Prajay to introduce himself and begin our webinar. Thanks, everyone.
Thank you, Katie. Hello, everyone. Thank you for joining today's webinar on FluoreSens 10. My name is Prajay Prajapati, and I'm an application engineer and scientist at Campbell Scientific. I have been with the company for over 2 years and working closely with FluoreSens 10. I am very excited to introduce you to this new system that is advanced automated system for measuring sun-induced chlorophyll fluorescence, in short form SIF. FluoreSens 10 is designed to provide high precision data on plant photosynthesis, helping researchers, agronomists, and environmental scientists monitor plant health, stress, and productivity in real time. This system can be used as a standalone system or can be paired with already existing covariance station. So this is how I have structured today's talk. First, I'll be talking about motivation for measuring SIF or having a SIF system, importance of SIF measurement, FluoreSens 10 specification, calibration measurement. I'll touch on SIF retrieval. Then I'll move on to SIF retrieval graphical user interface that we can provide to customers. Then I'll end with summarize the unique feature of FluoreSens 10 and contact information. So the main motivation and need for this system is that a system like this can help in better understanding of carbon balance and reduce uncertainty in GPP estimate. CO2 is the main greenhouse gas that can cause the warming of Earth atmosphere, and its current concentration is around 420 part per million, which is about 50% greater than that was in pre-industrial era. Its concentration has remained stable for thousands of years, but because of the deforestation and other human activity, its concentration has increased at an alarming rate. And with such increase in CO2 concentration, without drastic intervention, we can expect more solar energy to be trapped due to the greenhouse gas effect that's shown in the bottom graph. And this can result in extreme drought, precipitation, flooding, and heat waves. The main carbon sinks are the uptake by plant and the uptake by ocean. Land ecosystem remove about 1/4 of carbon emitted by human activities annually. Another quarter is being removed by ocean. And without these sinks, global warming would have proceeded at approximately double the speed. Whether a plant will keep on doing us favor by assimilating through photosynthesis, whether the emission will outpace that trend is still uncertain. So we need a better monitoring of CO2 and understanding of photosynthesis process, which will be crucial for assessing the Earth carbon balance and guiding policy changes. So SIF has this signal that's emitted by plant has the potential to help in monitoring CO2 by providing real-time insight into the plant photosynthesis, enabling researcher to monitor gross primary productivity, which is actually the carbon uptake by plants, and help in tracking the ecosystem productivity, detect stress, and improve the climate model. This SIF signal is a very weak signal, and it is about like 2% of absorb sunlight. About 56% is used in photochemistry for assimilating CO2. to sugars. About 11% is reflected, 20% is released as heat, and 11% is transmitted. This unique signal is emitted at a range of 650 nanometer to 800 nanometer and has a peak around 685 and 740 nanometer. So the SIF is can be directly linked to photosynthesis process. So it's the researcher have used this signal as a proxy for photosynthesis, and there are main two reaction that's involved in photosynthesis process, and the SIF is emitted in light reaction. In the light reaction, there are like two photosystems, photosystem 2 and photosystem 1, and in photosystem 2, the dissociation of water molecule will provide the electron, which when get the sunlight, the electron get excited, and as it come to ground state, will release the SIF signal. Part of the energy is transferred to PS1 through the protein molecules, and in PS1, the NADP is reduced to NADPH, and in this process, more hydrogen ion is built up in thylakoid of chloroplast, which will go to the stroma where the dark reaction take place. And in doing that, the ADP is converted to ATP. Both of these NADPH and ATP are energy molecules that are used to produce sugar from atmospheric CO2 during CO2 uptake. So why should we measure SIF? It's the only remotely detectable functional signal of photosynthesis that can be captured by instrument on ground or the sensor in satellite. It is inherently linked to photosynthetic process and thus a very good proxy for vegetation gross primary productivity. Can even be used as an input to compute gross primary productivity. And this signal is very responsive to plant growth, plant stress. So it's much more better index than other vegetation indices like NDVI, therefore can be used in early stress detection and warning, can also be used in drought and fire risk assessment. SIF can be measured, mostly measured by two methods. One is through the satellite and the other one is from the ground-based system. The interesting thing about the SIF measuring satellite is that apart from the FLEX, which will be launched in end of 2025 by European Space Agency, all other satellite where the sensor were designed to monitor the trace gases. But later the data was used for calculating SIF. So SIF calculated or like measured through a satellite can be used for estimating GPP in a global scale. But one of the constraint of the GPP estimated through satellite measurement is that because of the return period of the satellite, it has low resolution. Also, it's affected by cloud cover and atmospheric absorption. This gap can be fulfilled by measuring SIF at canopy level. So the ground-based SIF system stay like close to the vegetations. Also, it can be used for continuous and high frequency SIF measurement. So therefore, can capture the diurnal trend and it's not affected by cloud cover or temperature shift or atmospheric absorption. So so uh, so the measurement from SIF can be used as like ground truthing for measurement of GPP and SIF from satellite. So there are two main approaches for measuring SIF that's based on the ground. That's used for measuring the SIF from the tower. One is the single fiber optic approach, and the other one is two fiber optic approach. In the single fiber optic approach, like we did for FluoreSens 10, we use the single fiber optic cable to measure the signal coming from up, the solar signal, and the signal coming from the vegetation. And we use a diffuser or a cosine corrector. The And in doing that, that will maintain intensity of light the same throughout the pad. Uh, so also when we can, if this FluoreSens 10 system is integrated with EC system, there's a maximum or better footprint overlap between the EC measurement and SIF measurement. In the two fiber optic approach, there are fixed fiber optics they are looking up and looking down, and they require a switching mechanism to turn off the light from one side when it's measuring from the other, when it's measuring the signal from the other side. The advantage of this is that it uses cosine corrector for incoming sunlight and bare fiber for measuring the signal coming from the vegetation. So because of the lower field of view for the bare fiber, this system can measure a shift signal from individual tree, but it's not suitable when integrated with EC system. Also, the light transmission is altered because a switch or prism is used. So the irradiance calibration is no longer valid. So there should be a frequent calibration at each measurement sequence. So the FluoreSens 10 system is AC powered, and its power requirement is 130 to 150 watt. It's based on two spectrometer. The best model comes with just the QE Pro, that measures shift signal, and it ranges from 650 to 800 nanometer and has high resolution compared to the the spectrometer that measure vegetation indices. The vegetation indices measuring spectrometer is flame. It's much smaller, and its range is 400 to 900 nanometer with resolution of 3 nanometer. It's based on data logger and also on a fiber guide assembly that rotate up and down. And the enclosure where the spectrometer is placed is temperature controlled so that the internal TEC of the spectrometer can maintain the internal temperature of the spectrometer at -9 degrees centigrade. And this is required for reducing the thermal noise. So so the the user will get just two piece of equipment, just the enclosure and fiber guide assembly if they don't require the tripod. And the enclosure can be mounted independently in a single tripod, or can be installed in already established tower. There are just two cable that needs to be connected from fiber guide to the enclosure. One is the motor cable that's for communication. The other one is for the power. The one end of the fiber optic cable is attached with cosine corrector. This is a diffuser that's made up of opaline glass, and it increased the field of view by 180 degree. The other end is connected to the spectrometers with the SMA connectors. So as soon as this system is powered, light enters through the fiber optic cable, and it goes through the entrance slit of the spectrometer, then through the collimating lens, and the grating will split the light into its component part, and it will land on the detector. The detector is charge coupled device. The photon from the light will produce a charge which is converted to digital number, and this digital number needs to be converted to unit of irradiance, microwatt per meter square per second. And that will be the part of the post processing, and that can be done easily by using a graphical user interface, which I'll talk about in the later slide. So one of the other important thing for the measurement is the integration time. The integration time is optimized by the data logger code. The integration time is the duration of the exposure of light that's required for spectrometer to measure and hit default value that's of pixel count, that is 150 to 180. If the light is too bright, it will hit the default value or the threshold value pretty quickly, so the measurement is quick. But if the light condition is low or overcast condition, the system will wait until it hit this pixel count. So all of this process is automated and optimized by data logger code. The important step is another important step is the calibration. Calibration is required to convert the pixel count we measured from spectrometer to the unit of irradiance, and this is done by feeding the lamp light to spectrometer. This lamp light has known intensity for the known wavelength, and all the customer needs to do is use this graphical user interface that's based on RTMC, and just pause the system and bring the system mode to calibration, and the data is saved in the raw data file, which can be used later on in post-processing for calculating a conversion factor. Next feature that's available in the RTMC is monitoring the shift data in real time. So here, this graph is just the ratio of outgoing radiation divided by incoming radiation, and the peak you are seeing at 760 nanometer. That's the evidence that SIF is present in reflected signal. So what we are measuring is the incoming solar radiation and the reflected solar radiation shown by the blue line. And both of the spectra are absorbed at a particular band at 760 nanometer by oxygen molecule. But the reflected light, there's an infilling of a weak signal. About 80 to 90% is absorbed, but there is an infilling by SIF signal. So that's why we are able to see this peak at this particular band, which is a SIF signal. So the SIF data is saved in a spectra table, and the vegetation indices data is saved in flame output table. These are saved in a data logger. And what this table contain is timestamp, the position of the fiber guide assembly, uh, uh, and the light source, whether it's the lamp source or natural source, and also the pixel counts. The only difference between these two tables is the number of pixel counts. So the SIF measurement has 1044 pixel count, and the flame measurement has about 3046 pixel count, which is like specific to these two spectrometers. So retrieval of the SIF signal is challenging because it's a very weak signal. So we have to choose a wavelength where the bright light, the incoming bright light, is absorbed. And luckily, at certain band like 760 and 680 nanometer, there's an absorption band for oxygen molecule, and these bands are called oxygen A and oxygen B oxygen B bands, and At this band, most of the incoming solar radiation is absorbed, so we are able to see the SIF signal. That's a very weak signal. And the retrieval is based on the absorption band, and the method is called, one of the method is called Fraunhofer line depth method. And in this method, we find a value for just outside of the band and inside of the band for these two incoming and reflected light, and we use this equation which basically shows that the reflected light contains some portion of incoming sunlight and shift signal. And by assuming that for this narrow band, the wavelength at these 2 points are same, the reflectance is same, so is the fluorescence for this narrow band, and solving we can calculate the reflectance and the fluorescence. We also provide this graphical user interface, which is based on Python package, and all the user need to do is use two modules. One is the calibration module, the other one is SIF and vegetation indices calculation module. The calibration module, you can will import the data that was saved during the calibration and will calculate a file that has the conversion factor, and that can be imported in the SIF and vegetation indices calculation module, and also import the raw data and specify the output folder. Just choose one of or all of these retrieval methods. The SFM is spectral fitting method, and it's based on regression, and the SFLD, IFLD, all those are various forms of the FLD. And so this having a GUI makes the calculation really, really easy and simple for users. So this is the data that came out of the graphical user interface. And we can see this nice little diurnal trend, which shows that the sensor was able to capture the diurnal trend for these days. And we see there's no shift signal during the night time because this instrument doesn't measure, or like it waits for the light to be available for measuring the shift signal. And we also see the difference between all these retrieval methods, and having or developing a better method for estimating shift signal. It's still active area of research, and all these differences are consistent with the characteristics of this method, and this has been reported in literature. So to summarize the unique feature of FluoreSens 10 compared to other systems, it uses single fiber optic cable. What it maintains the same intensity of light throughout its light path, and as a result, you just need to calibrate it once in a year, or as soon as you detach the fiber optic cable from the spectrometer. It's based on data logger, so you can add other sensor as well, and there is a better synchronization between other sensor measurement from other sensor and SIF measurement. And we have a dedicated data logger code for that, so it makes measurement really quick. So every 4 seconds, actually it takes 0.5 seconds, but the additional time is required for the communication between the sensors and clearing the buffer. So other feature are, it's based on a proven technique. So we developed this sensor or this system with collaboration with Dr. Liu Honggu from Oak Ridge National Laboratory, and the prototype version, the original version of this system, has been used extensively at his site for measuring shift signal, and there are several papers that came out of that. Also, this system has just one fiber optic cable with diffuser with a cosine corrector. So there's a better footprint overlap between EC measurement and shift measurement if anyone want to integrate the shift measurement with the EC measurement. That's all I have from my side. If you want, or if you need more information, and if you want to discuss your application, then please let us know. And thank you for your attention. And I'll be happy to answer any question you have in chat. Katie?
Yeah, thanks so much, Prajay. That was great. Very interesting. We do have a question from Matthias Kuntz in the Q&A section, and he was asking, is the post-processing software open source so that you can adjust it to your needs?
Yeah, we can provide the the graphical user interface with the code as well, so they can use graphical user interface as well as the code in which they can make changes. So yeah, they can modify the changes so that it can be improved. They can modify the
Okay.
code so that they can make the improvements.
Okay, perfect. Thanks. And then we have another one from Shakir Adnan, and they are asking, what is the footprint of the measurement on the ground, and is it suitable for use on tree crops?
Yes, like so it the one of the requirement will be it has to be at the same level where the EC sensor is placed. So, and one study has shown there is a 70% overlap between the peak of the EC footprint and C footprint.
Okay. Um, and then we have another question from Matthias. Yes, one of the advantages was that you can easily attach other sensors, but the logger program is encrypted. So how do I add more sensors?
For now, like because of the contract agreement, we are able, I am able, or the Campbell Scientific is able to make those changes if you want to like discuss your application or the sensor you need.
Thanks, Prajay. We have another one from Adnan Yusuf. Thanks for a great presentation. I would like to know if this sensor comes with a pan tilt unit.
So the tilting is done by as I've shown in the one of the video, the fiber guide assembly itself tilts. So I don't think it require any pan tilting equipment or additional sensor. So the answer
Okay.
is no, it doesn't come with pan tilting
Okay,
sensor over it.
perfect. Let's see. Oh, yes. So the webinar, everyone will be emailed a link afterwards with a recording of the webinar. So you'll be able to go back, and if there's anything that you missed or anything that you want to watch again, you'll be able to do that. Let's see. And then we have another question. Have there been any research campaigns or scientific studies already carried out by the FluoreSens 10? So I know there have been some papers published on it. You can speak to that a bit more, Prajay.
Yes, like I have said in the almost last slide, there are like 3 or 4 papers that came out those studies. They made the sheaf measurement on the top of the canopy. Yeah, there are multiple studies that they have done using the original version of the sheaf unit.
Okay. Perfect. Let's see. I think we have another question. What are some ways that you can reduce uncertainties in the SIF data?
Uh, so one way would be like so if you put the gap between the canopy and the fiber guide assembly more than like above 10 meter or more than 10 meter, then you will need to make the correction for absorption by the aerosol. So one way would be to put as close as possible, or like at least below 10 meter above the, I mean, like the gap should be like at least like should be less than 10 meter, I would say. So that would be one way to reduce the uncertainty.
Okay, perfect. I'm having trouble if anyone's putting questions in the Q&A section. For some reason, those are not loading for me. So if you can put their questions in the chat. Um, oh, Ben answered that one. Um, so yeah, I think we'll do maybe one last question if someone wants to put that in the chat rather than in the Q&A, because for some reason those aren't loading for me. Feel free. We had someone saying thank you so much for a wonderful presentation, so that's great. Yeah, I think that is everything. I think we're going to end the question period here. So if anyone has any, oh, one more from Matthias. If I need correction aerosols, is the system working on forests?
I
Is there
can.
another way? Yeah, do you get that, Prajay?
Can you repeat the question again?
If I need correction aerosols, does the system work on forests? Because they'll be more than 10 meters from the canopy.
Yes, there are ways of there are paper that came out and there are algorithm available for making the correction. Yes, and I can provide the paper if somebody wants to get in touch with me.
Okay, perfect. Thank you. So thanks again, everyone. If you have any other questions or want some more information, please don't hesitate to reach out to Prajay or to Mark as well too. And you will be able to have a recording of this emailed to you afterwards. And yeah, thank you, everyone.
Thank you.
Thanks.